Okay, so we got our player animation working. It works kind of, but what we really, really need to do is get it to work relative to the direction the player is facing. That is the big missing component in this. So real quick, let's just think about that. What we have is once this loads. So what we have is our player, and let's just represent them by the circle. And our player is going to be facing a certain direction. So in this case, maybe our player is facing this way, and our player can move in any direction. So if our player is facing this way, and they're also moving in this direction, let's just use a different color for the movement. Okay. So red's going to be our movement. So if they're moving in this direction, then that means they need to be running forwards, right? Because relative to this direction, they're moving forwards. If they're moving in this direction, relative to this, they are moving backwards. Same thing with this and this. This is going to be left and right. And this will be changing based on whatever direction they're facing. So if they're facing the other direction now this becomes forwards. I'm sorry, this becomes backwards. So what was forwards is now backwards. This becomes forwards. Forwards, and this now becomes left and right. So if we think about it, what we want to do is given a rotation for our player. So if our player, again, let's just draw one more, they're looking in some direction. And we have some velocity. We want to know how much of this velocity is either, in the forward direction, negative forward again being backwards, and how much of this velocity is in the left and the right direction. So to do that, we are going to look at three concepts. I'm not going to get into the formula for these. I'm not going to get too much into the actual math of this. All I want to look at is what this is going to help us accomplish. The three concepts we are going to look at is one called normalizing. So normalize. We are going to look at the dot product. And by the way, the things we're talking about here are operations that we can perform on vectors, our speed, our positions on vectors. We are going to look at normalizing, dot product, and the cross product. So let's start with normalize first. All normalizing is taking a vector. So if we had a vector that was this long, it started 0, 0, and it went on to like 5, 5. It is taking this vector and shrinking it down into something that fits between 0 and 1 while still preserving the direction. So if we had a vector that goes like this, when it normalizes, it might look something like this. It still keeps the direction and it keeps its size relative, but it now fits between 0 and 1. So when we normalize a vector, it's just going to fit between 0 and 1. So real quick, let's just take a look at that. So what I've done is there is a link on your Blackboard to this web page that I've made. And there's just a few vector math concepts, the things we're going to talk about, normal, dot product, cross product. There's just a few little interactive, I guess you could call them just interactive pieces that will help us illustrate this. So when I click now and I draw a line, you can see that there's this blue line that's drawn. However, if we release the blue line and we look, this blue line is where I made the vector, and this red line represents the normalized vector. You can see that the red line fits between this first square. This entire little area is all going to be normalized, so you can see I'll make another one. It doesn't matter how long or short it is, you can see that that red line does not change. But it does keep the direction. It just it fits the vector between 0 and 1. I can even make it shorter than that, and it still fits it between 0 and 1. And I can draw as many vectors as I want, and you can see that it just fits between 0 and 1. And so the reason we use normalization is to take vectors of different kinds and be able to perform reasonable operations on them, because we are scaling them down to work, in the same kind of frame. In this case, when we think of our player velocity, our player runs at a max speed of 600. And so that means their velocity would be something huge, but we can normalize it, and that way we can get a value between 0 and 1. If you remember, our blend space is between 0 and 1. Well, this way, that's how we can work on it. And one very big reason for this is, imagine you had another character and you changed their speed from 600 to, say, 1,000. And that means in your blend space, if you were using those values, you need to go back in your blend space, change the maximum minimum to, be between 1,000. But in this case, when we normalize it, it'll always just come back down to 0 and 1. And we don't have to bother with the actual size of these vectors or the magnitude. So that's normalization. We're just going to use it to keep the vectors all kind of in check, make them between 0 and 1. That way we don't care about the size of the vector, because that's not as important as the direction of the vector. That's what we really care about. And so that's what normalizing is going to help us do. So now let's talk about the dot product. If I click on this, again, I'm not thinking of the math behind this. You can look up the formula. It's not very hard, but that's not the point. Given two vectors, so we have an A vector and a B vector, the dot product is going to tell us how much or how similar these vectors are, would be a good way of thinking about it. So as I move this A vector around, you can see that it projects a line onto this B vector, and the dot product tells us the length of this vector. You can see it says 33 right now, and that's what it tells us. So how much of A lies on B, that is what the dot product is giving us. Again, let's not try and focus on the math. Let's just think about why this will be useful for us. When I normalize the dot product, it's going to be between 0 and 1. So you can see there's a raw dot product. And as I increase the size of this vector, that affects the normal dot product. But the raw dot product, but the normalized dot product is not affected by the size. It is just the direction. And again, it's important to note. Let's see how that matters to us. Let's imagine this B direction is a direction our character is moving. They're moving in this direction. Let's imagine the B direction is the direction our character is facing. So they're facing in this direction, right? They're facing towards the left. If our A and B were doing the exact same direction, you can see the normalized dot product is 1, which means they're moving forward. And A represents the direction they're moving, which means B, or the B representing they're facing. The players are facing in this direction and they're moving in this direction. The normalized product is 1. So we can say that they're moving forwards. We know we should play the forwards animation. If they are moving backwards, so if they're facing in this left direction but they're moving right, the normalized dot product is -1, which means we know they should be moving backwards. Same thing, if they're perpendicular, the normalized dot product is 0, which means they're not moving forward or back. And in this case, that's true. They'll be facing in one direction. Relatively, they're moving left or they're moving right. And as we change the dot product, so it approaches 1 as they get similar. As they go away, it approaches 0. Then it approaches -1. So this also will give us the forward component. It's telling us how forward they're moving. If they're moving in this direction, for example, you can see this dot product is starting to approach 1. They're not moving forwards because it's not perfectly 1, but they're moving kind of forward. And if you think about, passing this along to our blend space, it's going to move them 0.75 on that forward animation, which is kind of what this should be, right? Because they're moving forward. They're just moving forward into another direction. And so now this takes into account the direction they're facing and the direction they're moving, and tells us, based on the direction they're facing, how much forward and backwardsness is there to that motion. So again, let's not think about the math behind it or really what it's doing. If we just rotate these, we can see how this normalized dot product is 1 when they're the same, -1 when they're opposite, 0 when they're perpendicular, and it just kind of goes between those values. So this is helping us see how much of a forward component is there for us. And that is the way we are going to be using it. And similar to the dot product, there's something called a cross product. Technically, there is slightly more to a cross product, but again, let's not focus on all of that. Let us just focus on what we want to be using it for. So same thing, like with that A and B vector, here we have an X and a Y vector. So let's assume the X, or, let's keep the same color code. Let's assume Y is the direction our character is facing, and X is the direction that our character is moving. So just as the dot product told us how much one vector lies on another vector, how similar they are per se, a cross product tells us how perpendicular two vectors are. And again, this is very useful for us. So if Y is the direction they're moving, and remember, this is going to tell us about how much to the right they're moving, how perpendicular they're moving to their look direction. So if X and Y are the same, and we look at our normalized cross product, again, it's not perfect here, you can see that it's 0, it's basically 0. If X and Y are opposite, it's basically -0. So again, 0. And what that means is that when we're facing in a direction and we're moving in that direction, there is no left and right movement to our character. If we're directly perpendicular, you can see it's 1 and -1. So 1 would be moving right, -1 would be moving left. So we can use this. We can take our character's rotation, we can get the dot product with their speed, we can use that to drive the X component of the animation, we can get the direction our character is facing, we can get the velocity that they're moving in, and we can use the cross product to represent to drive the Y component of their movement. And that's how we are going to get and that's how we're going to get our characters to move properly, to move in the direction that they're facing. So again, take some time, try this website out, just try these interactive tools out. There's also some videos in your resources to actually understand these concepts a little more. We are not super focused on the math behind everything. I just want you to understand the result that we're using this for. Cross product measures perpendicularity. Moving left and right in the direction you're facing is moving perpendicular to the direction that you're looking. Moving forward and back, again, we can use a dot product for that because it's going to measure similarity. When we're moving forward and looking in a direction, that's the same direction of look and same direction of movement, cross product of 1. If we move in the opposite direction, cross product of -1. If we move perpendicular, the cross product is 0. Or I'm sorry, the dot product is 0. So let's use this now in Unreal. So let's get out of here. And let's go back to our player blueprint. So let me go into Twin Stick Pawn, and we are going to affect this get velocity function. So we want to get the direction the player is facing. We can do that using get actor forward vector. And first thing is first, let's do the first thing we talked about, which was to normalize it. And let's normalize both these vectors. And then if we just pull a pin out and we search dot, there you go. We have the dot product. And so this is going to tell us how forward we're moving. We're going to do a dot product between the normalized forward vector and the normalized velocity. Same thing, we're going to do a cross product between the normalized forward vector and the normalized velocity. We are going to make a new vector out of that, with the X being the dot product like we talked about, because X is the forward axis, and the Y being the cross product. The cross product comes out as a 3D, like as a 3D vector, but if we split the struct, we only need the Z component for it, because we are measuring how perpendicular something is between the XY plane. And so, anything that lays on it, it's the Z component's the only thing that can be perpendicular to X and Y in this case. So if we were to print X and Y component out, they would be 0. The Z is the only thing that's going to hold a value. Okay, so all we need to do is take this and use it to drive our animation. Let's try it out. Let's plug that in there and compile it. Make sure everything is saved, and let's go try it out. Okay. So first, let's see if things are working just as normal. Forward, backwards, left, right. Perfect. Okay, I'm going to face in the right direction, and if I hit D, I should be moving forwards, which is what we see. If I hit A, I'm moving backwards. If I hit W, I'm going to be moving towards the left, and S towards the right. And so just like that, you can see now we're going backwards, left, forward, and now our character perfectly suits the direction, the animation that plays relative to their look to wherever they're looking. So things actually look a lot better now, and our character looks very smooth now. In fact, this looks and feels like a good character now because the animations line up with whatever the player is doing, and it really looks professional. So again, I know this was a little long, or if not long-winded. If you guys haven't experienced these concepts of normalizing dot and cross products, this might come across as a little complicated. It's not. Let's not get bogged down with the math of it, but just again understanding how these are useful. You would actually find dot products are used a lot when it comes to game design because measuring how similar two vectors are is a very useful thing to do. Anyway, I hope this video is helpful in getting our character up and running. Thank you guys for watching.